Had such a delightful time. I've had such a delightful time chatting with the people that I've been fortunate to chat with today. Thank you so much for the invitation. And oh, I should probably click OK so that this is not here for, it's hard mode. Okay. Because I think I lost my cursor.
Maybe it's on the other side, left side.
When I bring it over, it disappears. We're gonna do this.
Oh,
I saw it. It went really fast. I'm so glad that this is being recorded. Okay, good. We can do it.
Nice.
Guys, I can't click okay. Let's see. Oh, maybe it's because I made things fly.
Okay.
We can do this. Thanks for everyone's patience. Okay, good. Now let's talk. All right, so today I am going to hopefully convince you that understanding how binary black holes of the stellar origin kind forming is actually a multi-messenger and multi-band puzzle. Before we get started, I love to be a little bit chaotic and maybe a little bit like aggressive. I would argue that even though binary stars may not be the thing that you think about every day, soon you will either reach a state in your research where they are a limiting noise source or they are already a critical component of your research in some way or another. Since I got my PhD in 2018, I've never had a visit yet where I wasn't able to connect binary stars to something that is tacitly important to any department that I've been in. And the reason for this is because galaxy evolution, I just read that off the slide, but galaxies are often driven by the stars that form them. The feedback from massive stars absolutely play a significant role. When it comes to making stellar origin compact objects, binary stars are absolutely the thing doing that. When it comes to things like star and planet formation, it turns out that if you form planets, you're probably not going to form binary stars and vice versa, which is a really interesting field of research that's coming on. And when it comes to both exoplanet populations and things like measuring clumpy dark matter, binary stars turn out to be the most annoying things in your data sets because they mask as companions or little extra wiggles that you might think are going on. So genuinely and truly, I think if we haven't had the chance to talk yet and you want one thing to come up with to talk to me about, try to think of a way that binary stars doesn't matter to your science, because I'm certain that that will be a fun conversation, and I'm certain I can convince you that they're in there somewhere. I recognize that maybe not everyone has had the pleasure of going through how binary star evolution works from a theoretical perspective, or rather maybe hasn't thought about it from start to finish, how you would make a binary black hole. So to ensure that we're all on the same page, I'm going to give you a little bit of a walkthrough for how I study binary black hole formation and the degree of physical accuracy in my models as it is, because it is largely cartoony at present day, and hopefully by the end of the talk you'll understand why. So in the models that I run, if you're going to make a binary black hole merger, you're going to start out with two massive stars, and while those two massive stars are on the main sequence, they are either going to evolve completely isolated like you see here. In this case, tidal evolution might be playing a role in changing the orbital period evolution. It also might be changing the orbital eccentricity, and wind mass loss is going to play a fairly significant role in stripping the envelopes of these stars a bit. As the stars continue on in their evolution, the more massive star is going to exhaust the hydrogen in its core and increase its radius significantly, filling what's called its Roche lobe. And when it does so, that Roche overflow can remain stable both on thermal or dynamical timescales, eventually leading to a significant, usually amount of mass that is donated to its companion. Often we'll get a mass ratio reversal here through stable mass transfer. where we end up with a massive star and a stripped helium companion. The evolution of that stripped helium companion is much faster than the main sequence evolution and rapidly will hit core collapse, where a compact object is formed. Whether or not this compact object forms through an energetic supernova explosion that imparts a natal kick to the neutron star or black hole is a very uncertain, open question in physics. If we figure that out, we're gonna learn a lot of things, and if anybody does figure that out, please let me know. But one thing that we know for certain is that whatever happens in this compact object formation is going to be imprinted in both the orbital period and the eccentricity of this binary system at this phase. Okay, so now we've got a black hole or a neutron star, you could have, with a massive star companion. Eventually that companion will exhaust the hydrogen in its core and it could go into a stable mass transfer as well. The main difference between this stable mass transfer and this stable mass transfer is the Eddington limit of the accretor. In the first case, you can donate a boatload of mass, sometimes 20 or 30 solar masses of material. In this case, we're pretty sure that the black hole has a pretty strong Eddington limit such that you're not going to accrete that much material. So this is going to have an effect on the orbital evolution that you might see between these two stages. Good. Okay, this does, however, eventually, oh, question, yeah, go.
How, do you always get mass transfer? Like what, how common is this? Is this always, or is this rare? Is this?
Hold your question.
Okay.
We'll get there. Ooh, we'll get there. I love it. Okay, good. So we're eventually gonna strip that envelope, leaving behind a stripped helium core with the compact object companion. We can get core collapse. Again, the kick may or may not occur, imprint into the orbital period and eccentricity of this binary. Once we hit this stage, gravitational waves take over, shrink and circularize your binary until you get a merger. This is one pathway that we can take. And the pathway that we take depends on the physical response of the star losing mass. So if the envelope structure is convective, it's highly likely that this is not going to be the path that we take. Instead, for example, if this envelope structure here is convective, you might not remain stable where the radius of the star tracks its rho slope, and instead you'll go into a dynamically unstable evolution that we often call common envelope. Common envelope can also occur if the orbital evolution happens on timescales that are so fast that the orbit responds more quickly than the star can respond as well. So it's both envelope structure as well as orbital evolution that determine whether we take each path. The main difference between this path and this path is that we're pretty sure that this happens on the dynamical timescale, maybe, who knows for sure, but we're pretty sure that it happens faster than this one. So in our code, this step happens instantaneously. In other codes, maybe not so realistic. Nonetheless, we're going to strip that envelope, leave behind, on average, much closer binaries that form much closer double compact objects, which usually will also merge on faster timescales. Cool? Okay, this is cartoony, but there is physics in every stage. This was written down in the 1960s and remains roughly the same state as it was theoretically written in the 1960s. And there's a reason for that. I think you had a question, maybe. Yeah.
But just before you go on, so those are all massive star systems. And how often they're actually in like triple and multiple?
Yeah. Oh, okay. I should make a statement at the beginning that says I cannot hold more than two objects in my brain at one time.
Good. Me neither.
This can be modulated by triple stars. That said, those triple stars are usually in hierarchical configurations. They're almost never in any other configuration because that's not dynamically stable. And what triples can do is accelerate these types of interaction processes largely. They can also induce high eccentricities in the binaries. It is a thing that happens. How often it happens, Lord knows, as far as I'm concerned. Yeah.
Hi, so can I just ask, so with the common envelope phase, where you have like this metal compact object, is there a limit to what the mass of the black hole can be during that common envelope? As in like, what the mass of black hole is going into it, or is it whatever?
It's whatever comes out from here. So it is predetermined by our binary evolution model and the initial conditions of the system, but we don't have any hardcore like limits on that necessarily. The orbital response to this Roche overflow is what will determine, the choice that you take. Yeah.
I guess, with a very large mass ratio, you might get a merger, prompt merger.
Yeah.
Instead of, leaving behind a compact binary.
Absolutely. That's an excellent point and something that I always forget to say. There is a secret third option always in this choice, which is a stellar merger. I never put that on my screen because it doesn't ever make one of these. Right? If you do a stellar merger, you're never gonna have a binary black hole merger. That said, much more likely to get a merger here in many cases than a successful common envelope projection. Yeah, good. Okay. Other things? No, good, cool. Okay, to bring us into reality. So this is largely a description of what I think about all day, every day in code fashion. And the reason that I'm still doing this, even though people like Ron and Bowden Paczynski literally wrote this down a way long time before I was born, is because these phases have only been directly observed. This is the early one, that's the easiest. You'll note lots of 20s in here. We have not had huge aggregate binary population observations for which we can confront our models with until now, genuinely. The vast majority of the work that I do has been seeded in predictions and motivations for gravitational wave detectors, because why would you build a detector for something that doesn't happen very often? How do we decide if it happens very often? We simulate every star in the universe and count. That's why we do what we do. Okay, good. But now is a really good time to do this because not only do we have gravitational wave observations, which I'll tell you about, but there are other phases of evolution that are being teased out of the data. And so now is 100% the time to be working on binary stars as far as I'm concerned.
And
Yeah.
like now it's really obvious why this matters with like exoplanets and gravitational waves and cosmology and all that. In the 60s, why was this cool?
Still gravitational waves.
It was.
100%.
Huh.
If you look at all of the binary evolution papers, it's often, we figured out nucleosynthesis is what is driving the stellar evolution. That makes black holes. Black holes could merge and make gravitational waves. It's like boom, 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 every single time. It's
Huh.
kind of cool. You can see it in all the papers. Yeah,
Interesting.
There's also a huge community on X-ray binaries.
yeah, totally. And similar timing though, of like, they get to here and then it was driven by observations of like explaining these like weirdo systems. But I should look this up because I don't know when the direct detection of the first X-ray binary was, but I think gravitational wave predictions might predate.
Would have been
That.
1963 with the
Yeah.
very first, rocket experiment by Giacomo.
Right, I
Yeah.
knew it was the 60s, so I think it's similar. I think the Paczynski paper might be 1967, but similar
Yeah,
ideas.
so excellent.
Yeah.
I knew it was a sounding rocket, I just don't remember the year. Thank you, I appreciate that. Okay, good. So this is what I think about. Now for completeness, of course, this can also happen. It could be the case that your envelope is such that you go straight into a common envelope here. Maybe the orbit responds in a certain way. But by and large, this is all you need to have in your head if you're gonna make a binary black hole merger with isolated binaries. Easy, right? If we write it in words, you take away anything from this talk, take away these points. Roche overflow mass transfer is far and away the dominant uncertainty in how binary stars work. If we understand how Roche overflow mass transfer works across all mass scales and all compositions, we're done and dusted, more or less. That's gonna be a long time coming, probably. To a secondary degree, for compact objects, that compact object formation mechanism is also playing a significant role. And the reason for that is because if you have strong natal kicks, you are likely to unbind something like 90% of the binaries that you start out with before a supernova. So if you unbind all the binaries, compact object formation will win over mass transfer. The way that I study these things is through a method called binary population synthesis, where we try to fold in all of these physical processes that I've talked to you about, as well as things like wind mass loss, magnetic braking, tides, like I mentioned, anything that you can think of that might alter the evolution of the binaries. We come up with a prescription to put them in our codes and simulate everything to see what comes out. That's the general idea. The code that I use is a code called Cosmic, which is fantastically difficult to Google because I was a grad student when I named it. And I didn't think that far in advance. So if you would like to Google the code, I would recommend that you Google Cosmic, pops in, and it should come up easily. Cosmic was fully released in a code paper in 2020. It was the first open source code that you could access in Python. Prior to this, the other open source code that you could use to do PopSynth was called BSE. And to do it, you had to do Fortran. I don't know, Fortran's fine. I don't know why it was such a problem, but what I wanted to do was make sure that everybody could use the code. So we spent a lot of time developing it in Python, opening everything up, making sure that people could trust what was going in on these simulations because they knew what was happening. So if you have an opinion about what we should or shouldn't be including in our models, I'm very excited to hear from you because we're a bring everyone in community type thing. One of the things that sets Cosmic apart as well is that we actually do bit by bit comparisons with globular cluster dynamics through a code called CMC that was also developed through Northwestern. What that means is that all of the stars in the globular cluster simulations that are run with CMC are actually evolved with Cosmic. So you can do really nice comparisons between the two. Since its release, Cosmic has been used in 100 studies. I think this is probably the last time that I will show a slide with all of the names on it officially. We hit 100 over the weekend, which is pretty exciting. It's been used for studying just nice normal stellar populations. We've had it used in X-ray binaries, accreting white dwarf binaries, detached double white dwarfs for LISA, all the types of black holes, and you can see the globular clusters kind of cleaning up in here. Smadar Nawaz has also put it in with some of the awesome galactic center work that her group has been doing as well. And what I hope to convey to you is that you can actually pick it up and use it, even if you aren't one of the developers. And the reason for this is because I've highlighted all of the people who are not developers in any way on the code in green. So these are people who use the code, and I found out about it because I saw a citation. So you really, like, you don't even email me. Just use the code, enjoy it, use it. That's what I love. Okay. Today I'm focusing on, oh, I didn't highlight it, these guys, binary black holes, but I will highlight just very quickly, I don't discriminate on mass or type of messenger. I'm super stoked to talk about LISA and white dwarfs and their progenitors. I think that that's a really interesting science case. There's only so many minutes in this talk. I'm also very happy to chat with folks who are interested in getting involved in open source software development. That's something that I like to spend a lot of my time thinking about. And in particular, I want to highlight one code package that we just got out with Tom Wag recently, which I won't be talking about any results from here, but if you're interested in any types of binary compact object populations where you can self-consistently calculate how those populations evolve through a galactic potential, if you want to know where the compact objects are in a galaxy, Tom can tell you. In particular, if you treat only the compact objects as singles and without a potential, you're going to get the wrong answer. You have to really take into account binaries and galaxy dynamics to get everything right. And a second code project that I've been working on with Pooja and Agrawal is incorporating Matisse. which does much better single star evolution under the hood of our models. And in particular, we can implement very different stellar evolution models in the back end of Cosmic. So if you have your favorite stellar evolution model, I can help you set those grids up, and we'll get really nice different radius evolution, which affects all of the cartoony things that I showed you before. So if you are somebody who had an opinion about these SSE Hurley tracks prior to this talk, and you didn't want to use the code because those ones suck, we have awesome new ones for you to play with. Cool. Okay, let's actually talk about binary black holes now. That's a long interlude. Sorry for the mega introduction, but, okay, if you have been living under a rock for the last 10 years, you will be surprised to hear that we have detected gravitational waves from merging pairs of black holes and neutron stars. The first detection was a binary black hole that goes by the name of 150914. That means that it was discovered on September 14th, 2015. There was also a binary neutron star discovery in 2017. And yeah, I have a joke here. This one gave us a Nobel Prize. Cool, very good. Congratulations to Kip and Barry and Ray. This one proved that 5,000 astronomers can write the paper together. I am an author on none of them. Okay, good. So we have these merging pairs of binary black holes. They are detected by ground-based detectors that are 4 kilometers on the side. Those 4 kilometer on the side lasers are sensitive to kilohertz gravitational waves, which means that they are observing mergers of binary black holes that are orbiting each other roughly 1,000 times per second by the time they merge. Very nice. When we observe these systems, we get our gravitational wave observables. In particular, we don't measure individual masses. We measure very well this quantity called the Chirk mass. For systems that have a near equal mass ratio, this is effectively the total mass of the system. Sometimes we might measure the eccentricity of the system, but if we're being completely honest with one another, ground-based detectors are not going to do this particularly well for binary black hole systems because it's extremely difficult to disentangle the effects of eccentricity and this spin that is measured of the black holes, where the spin that's measured is actually mostly this green arrow here, chi effective. Chi effective is the mass-weighted spin projected onto the orbital angular momentum axis. It doesn't tell us a lot about the spins. That's the thing to take away from here. The thing that we measure very, very well is this Chirk mass. Okay, so had you seen me give a talk in 2015, I would have told you gravitational waves are going to tell us exactly how binary stars interact with one another, because all of the interactions that happen in the cartoon that I showed you imprint very strongly in this mass distribution. It's 2024, almost 2025. I am not here to tell you that today, and there's a reason for that. It turns out that when we detected gravitational waves in 2015, there were roughly 2 formation channels that existed at the time. We thought maybe these things come from isolated binaries. We see those all around our galaxy, sure. And maybe they come from globular clusters. Easy. So everyone thought we're going to just compare against those 2. That is not the case anymore in the year 2024. There are many, many formation environments. I told you about isolated binaries. They do imprint specific features. In particular, we do not predict any very massive black holes because there's a feature called parainstability supernova in stellar evolution that will completely blow up a massive star that would make a black hole bigger than that mass. So that's our one very strongly defining feature. We mostly like mass ratios close to 1. Maybe the chi effective is big. How do black holes get spin? Nobody on this planet knows, as far as I'm aware. So tough to say. There could be triples. This is where the triples come in. Triples, by and large, are going to have the same parent stability supernova issue, but they come with very high eccentricities because that tertiary companion can excite large eccentricities on the center binary. We know many massive stars form in open clusters. That's where we see all the massive stars when we look for them. In this case, you could have stellar mergers or secondary binary black hole mergers that get you some more massive binaries. In general, you can also get some kind of weird mass ratio systems, and they tend to have pretty short delay times. If we make really big clusters, like globular clusters, dynamics takes over. You get lots of repeated mergers, potentially. You have very strongly peaked mass ratios towards 1. You get a nice large eccentricity. And because these systems are dynamically put together from random black holes, we're almost certain that the spin distribution should be completely symmetric. There's nothing that's making those spins line up with one another. Okay, and the last 2 formation channels have recently stormed the scene and seriously blown open the parameter space on what you can do. This one is binary black holes and AGN disks. This is kind of just like vibes at this point, if I'm completely honest, because AGN are so hard to simulate, and then you put stars in them. So people are doing some really awesome, careful work to try to figure out what this looks like, because there are a lot of AGN disks out in the universe. Almost certainly there are compact objects around them, so this could be playing a significant role. And finally, we can close the circle, because if you have unstable mass transfer or non-conservative mass transfer, you're almost certainly going to make a circumbinary disk. So we're back to disk physics. Yeah.
Have there actually been any observations of like an AGN breaking up because of a compact merger in the disk or something?
Yes, there is one candidate of an AGN flare in ZTF data, coincident with the most massive binary black hole merger that we've seen to date, 1905-21. Is it real? Nobody's betting anything on it right now, because like it could be just another flicker on the AGM. The way that you would confirm that it's real is that models predict that if you get a merger here, you're going to get a nice little merger kick that shoots it out of the disk, and then we should see it come and puncture back through the disk and make another little brightening sometime in the future. There's a nice paper led by, oh no, I can't think of the name. There's a nice paper from the ZTF group led by Matthew Graham, that's his name. The prediction for when that's coming is 10 to like 500 years. Because it's really hard. They're not doing anything wrong. There is nothing wrong with their models. It's a really hard problem to solve. So who knows? Okay. All right, so there's many, many formation environments. We can make these things damn near anywhere in the universe. Unfortunately, understanding the physical processes that shape the stellar remnants coming from just this one depends on understanding the effects of the environment from everything else. Further, if we don't understand every single thing, then our population inference becomes useless. Cool. This is why nobody's trying to do this anymore in the way that we said that we would in our grants. So there are some things that we are doing seriously within our community to try to solve this. And what's happening is most of the people in our community, in each respective community, are going back and very carefully assessing what features in our models are only in our models. Because right now I can give you vibes like I gave you here, but we haven't stressed our models to the edge to see what the limits of those are. A beautiful example of this is Lika van Soen's work. So these are common envelope channel where the black holes went through at least one common envelope. This is stable only mass transfer channels. On the top row, she's varying the width of the metallicity distribution that stars form with across the universe. That's the purple. And then here, she's varying the mean metallicity growth with cosmic time. And the lines the red lines vary significantly. She's comparing against the rate distribution of the black hole mass spectrum. And yeah, so you can see the lines vary from her predictions pretty significantly, but the features, the mass bumps, are stable to metallicity. We did not know that this was true until Lika did this. So that means that we can probably use mass bumps as a way to compare our models against the measured mass features. That was not a given prior to Lika's study. After she presented this at a colloquium earlier this year, we sat down and with Gina Chen, a student working with me at CMU, we decided to investigate how we could make this work better with the LIGO distribution, because clearly this giant bump between 10 and 40 solar masses is not particularly showing up in our data. So what Gina has done is look at changing the stable mass transfer assumptions. Specifically, this is the degree of how conservative the mass transfer is between the binaries to see how our models affect those bumps. And we can see that we can absolutely hide our 20 solar mass hump that comes out in the data by changing the conservativeness of the mass transfer. This was not something that we thought to do until Lika had done this study first. So I think a lot of what we're going to be doing over the next few years are these feature studies where we say, if you believe that the binary black holes come from isolated binaries, your stable mass transfer assumptions must be that they are at least not perfectly conservative, because that is highly disfavored. That's a thing that we can say for sure, which thank God we can say something. Yeah.
So what are the implications on that level of common envelope systems for this form?
Yes, love this question. Zero.
Common envelopes, they're gone.
We did not consider common envelopes at all in this study. We're just zooming in on this one channel to just understand that one feature. There is a growing body of work that suggests that common envelopes between massive stars are maybe less common than we might think, based on detailed stellar evolution models that have been run. That remains to be completely seen. We're pretty sure stable mass transfer happens at least some of the time. So incremental progress where we can make it. Yeah. Good. This is about as far as I am taking it with LIGO populations because the formation channels are tough. So there are some other populations that make this both a multi-messenger and multi-band puzzle. I'll very quickly take you through why I believe that this is a multi-band puzzle, and you'll see why we're only talking about it quickly, because it's not going to happen for a while. The time scale for this is 15 years, because in order to do a multi-band measurement, we're going to have to do something called fly LISA, which has been a feat of humanity since as long as we've been trying to make LIGO. Except LISA has already been canceled once and brought back from the dead. So it's not going to be easy, but it will be worth it. So LISA is a space-based, oh wait, let's see, before I get there. The reason that it's important to consider multiband sources is because if you form double compact objects like binary black holes with residual eccentricity, by the time it makes it all the way to the kilohertz band, almost all of the eccentricity is gone, no matter what you do. You can form these with an eccentricity of 0.99999, and it will be 1 part in 10 to the 5 by the time you get here. So it's not just that these detectors are not so good at measuring eccentricity, it's that there isn't any to be seen in the first place. However, LISA is going to be sensitive to gravitational waves at much lower frequencies. That means wider orbits where there's more residual eccentricity to be observed. The reason that this works is because it is a 2.5 million kilometer long detector. It is enormo. It has to be launched into space because it's so big. The planned launch is currently 2035. When I started grad school in 2013, the planned launch was canceled. So we're in a much better state than we have been ever before. To build confidence, I will tell you that ESA is who is doing the development of LISA, and ESA doesn't let missions slip the same way that NASA does. They'll find somebody else to do it faster. So this 2035 might slip a little bit, but it's not gonna slip the same way that we would expect JWST to do it. Okay. So LISA flies, and it's looking for binary black holes. Because of the lower frequency, its sensitivity in distance is significantly reduced, but with that distance sensitivity comes an enormous benefit for understanding the eccentricity versus frequency evolution of binaries. In particular, I'm showing you here a bunch of simulated binaries that start out at high eccentricities, low frequencies. Gravitational waves shrink and circularize them on this nice power law. If you simulate them from different channels of isolated binaries and globular clusters, you can see that there's a little bit of a split in the eccentricity. LISA will very easily measure the orbital period evolution of everything above this line, and it will very easily measure the eccentricity of most of the binaries above this line and all of the binaries of this line. That means that some of these binary black holes will have observable eccentricity within the LISA band. Because you can measure the gravitational wave evolution, you actually also get a chirp mass measurement. And what you can see is that all of our models predict very different features in eccentricity and mass space. Every single channel predicts something different. So when LISA flies, it is not unlikely that it will tell us more about binary black hole formation than ground-based detectors do, because the eccentricity is so imprinted in the formation environments. That's all I'm gonna say about LISA. I don't have the heart to tell any grad students to work on something that's not going to even be close to launching during their tenure. So for now, this is my baby. I think about LISA things. In 10 years, we'll all be thinking about LISA. It's kind of the take I have there.
We have a naive question. So here, I maybe I misunderstood it, but you said you're gonna see evolution of this system. So does that mean LISA has to be performing targeted observations?
No.
So once it's triggered, it can continue to observe that source.
Yep, LISA is a single stream of data that you take time series 1 second observations of stretches and squashes, the same way that LIGO does, and you do a giant Fourier transform at the end of it, and all of the gravitational wave frequencies come out in a frequency comb. And the reason that we can measure chirp masses from LISA sources is because you see those frequency combs move at a rate that is consistent with the gravitational wave emission.
And what ratio range are we talking about here?
These are up to a gigaparsec.
Okay.
Is all, very nearby for LISA.
Thank you.
You can calculate the rate based on the LIGO rate. This is a paper that is languishing in this laptop. It's about 8, if the 8 for a 6-year duration mission. Yeah, it's not many, but every single one of those will have a measured eccentricity with them. Yeah, there was another question.
Yeah, two things. Quick one, does one CE just mean with common envelope?
Yeah, one common envelope, no common envelopes.
And
That's right.
the other thing is, so, is it right that LISA also measures this the high effective projectile?
I love that question. These systems, I think, are likely too wide to measure any type of chi effective, because you need to see spin orbit coupling in the waveform of the gravitational wave, and in this case, it's just not strong enough yet, because the orbits aren't close enough.
So how does the measurement differ, and why can you do it with LISA and not with LIGO for?
Oh, because the gravitational wave frequency evolution also depends on the eccentricity.
Oh.
Yep, yeah. Excellent. Okay, good. We've had so many lovely questions that I'm gonna look at how many slides I have left. And I think we're gonna skip I will tell you very quickly, if you're interested in targeted modeling of individual binaries, come talk to me. We have a super cool, fun code base that does Monte Carlo sampling of individual systems. If you have a weirdo binary that shows up in some data set that you're not sure about, I would love to help you figure out what the binary evolution models that make that. We don't have time to talk about it today. What we do have time to talk about is this. I think the thing that we are going to learn the most about in the next 5 years when it comes to binary evolution is going to be coming from these compact objects and complementary populations. And so here is where I'm going to try to soapbox just a little bit and hopefully convince the people who review grants in the room that this is realistic. A lot of money is going into multi-messenger science these days because 7 years ago, we found the most incredible multi-messenger source there ever was, the binary neutron star merger. It was detected simultaneously with gravitational waves, gamma ray bursts, and then over months, the entire electromagnetic spectrum. That is one type of multi-messenger source, but what I'm hoping to convince you of today is that multi-messenger science does not require concurrence and observations. We don't need every single person working on this stuff to have a pager that tells them to go point their telescope now or risk losing a paper. But also, we don't necessarily need to only consider multi-messenger sources at a single evolutionary state. The reason for this, I hope, is pretty clear, because compact binary systems go through many evolutionary states that can be observed as multi-messenger sources. And in order to put all of this together, we recognize that as a system goes from being a detached binary star to a black hole plus a star to an accreting binary and then a gravitational wave source, as this happens, the size of the orbit decreases substantially. So we're going to use some relatively separate tools, but if we apply all of our multi-messenger science that we can across this evolution, then we can maybe put it all together to learn how binary stars work. That's the story I'm shipping right now. Cool. The thing that I want to tell you about today in this talk is this one phase here, the detached black hole plus star binaries. These have officially been named by Karim El-Badri to be dormant black hole binaries. Apologies if there are X-ray observers in the room, because dormant black hole binary means something else to the X-ray community. However, these systems are and will always in this state remain dormant. And the reason for that is because we find them by watching their nice, bright stellar companions orbit nothing. They're orbiting something, we don't see what it is. We don't see any interaction with the compact object itself. One of the ways that we can do this is they're often called radial velocity black hole binaries. And the idea here is you measure the radial velocity of the star. It comes along with this very horribly annoying inclination degeneracy, but you can measure black hole masses relative to a modeled luminous companion mass to pretty spectacular degrees. This is not a new thing that Jeff Andrews and I wrote down for the first time, obviously. Kepler wrote this down a long time ago, and Virginia Trimble and Kip Thorne actually have papers on this from the 60s as well. Why didn't we find all of them in the 60s? It's very difficult to convince anybody to point your big, beautiful, large glass telescopes at dinky stars many times. That just is like not the story for a while, but now it's the story. In particular, there was a wonderful survey done with Muse where this globular cluster, NGC 3201, was stared at for a very long time, and two black hole candidates were turned out. You can see here, one is a pretty short period binary, one is a pretty long period binary. We have beautiful mass constraints on both of the stars. A nice thing is that the globular cluster models, CMC, specifically that Saurav Chatterjee and Kyle Kramer ran show that to produce this globular cluster with the observed radius profile, as well as a consistent rate of black holes with stellar companions like this, you have to have something like 100 black holes in the core here. That's nice because it tells a beautiful story of how globular clusters could make gravitational wave sources. And we're picking out many different evolutionary states to do that. We could only tell that story if we look with EM data to find these things.
So,
Yeah.
So here, the black holes are still dormant, right?
That's right.
But for this globular cluster, we also observe X-ray binaries.
Yeah.
So how do they compare the population wise?
Yeah, they, let's see. I don't think that they looked at NGC 3201 with the X-ray binaries. The person that I can tell you who is doing the most with X-ray binaries is Claire Yee in the group, and she's looking mostly at pulsars rather than black hole X-ray binaries. And she is finding a similar general story in that the pulsars tend to occupy a little bit farther out in the cluster because of this dynamical mass segregation story that everything is pinned to. But absolutely, people are looking at the X-ray binaries there as well. Yeah. Cool. A different radial velocity survey, the VLT Flames Tarantula Survey, or VFTS, has recently turned out this nice binary here, VFTS 243. This is a source that's in the Large Magellanic Cloud, and the paper was led by Tomer Shinar. This is a little bit tougher to do some mass constraints on because 10 solar mass stars are quite a bit more difficult to model than a 1 solar mass star, generally speaking. However, this is basically a perfect pre-galactic X-ray binary analog. It fits right in nicely with the rest of the galactic population, except for the fact that it has a bit lower metallicity. Cool. We should start to turn out more of these radial velocity survey type sources as SDSS-5 data comes online. I know that Jennifer Johnson with the Milky Way Mapper is interested in doing this type of stuff. I'm terrified of spectroscopic surveys in general. I'm also not a member of SDSS-5. So I probably am not going to be doing any of that, but keep your eyes peeled for that. The part where I'm hoping to jump in over the next few years is on the astrometric side. And so here, same idea, you're going to measure the bright star orbiting a dark companion. But in this case, the astrometry tells you the semi-major axis of your luminous companion. You can do some very simple orbital dynamics to get, without an inclination degeneracy, a black hole mass. So this is a really nice way to pick out candidates, potentially, spoiler, it is, for black holes with bright star companions. The reason that this is going to work is because Gaia is currently measuring the positions and velocities of over 1 million binaries in the galaxy. And as it does so, the binaries do, this is just a fun graphic to kind of build intuition. This is not how people actually do this science, but it's cute and it's nice and it builds intuition, so I still show it. What I'm showing is as you increase from left to right, the orbital period of the binary increases logarithmically. And so the red arrow shows the center of mass motion of the binary, and you can see on very wide orbits, we don't see anything about the binary. What we're seeing is these epicycles due to the parallax motion of the Earth, or Gaia. Here, the binary gives you the nice cute epicycles. In here, you might think, oh my God, how do we measure anything? It's always a year. So you just subtract a year out, you get beautiful black hole orbits out of this stuff. With Chirag Chawla and his thesis advisor, Saurav Chatterjee, we have been working to simulate the Milky Way's dormant compact object binary population to try to get out ahead of what Gaia is going to see. In particular, Chirag has been taking metallicity dependent ages and positions of stars in a Milky Way-like galaxy from the latte suite, combines it with binary evolution with cosmic, and then we apply a pretty faithful population selection cut from Gaia to see what comes out. In particular, we're finding from our models a couple of things. First and foremost, most black hole binaries that are observable by Gaia will likely be post-common envelope binaries. The reason for this is because most stars that are still stars in our galaxy are low mass today. Anything that was a massive star more than 40 million years ago is not a massive star anymore. So the bulk of the stars that Gaia sees are low mass stars. If you put a low mass star next to a very massive companion that's going to make a black hole, that almost always leads to a common envelope. This is illustrated very clearly in this diagram where I'm showing log orbital period on a year scale here for two different configurations, black hole main sequence and black hole post main sequence. In green are the systems that don't go through a common envelope. They're all at wide periods and they don't go through a common envelope because they don't interact at all. Anything that is below this 10-year line, the Gaia observation duration, more or less has gone through a common envelope because there was a Roche overflow interaction. This is also shown as the big blobs in this other giant figure. To the right, no interaction, no common envelope. To the left, common envelope. The other thing that we know for certain from our models, at least, is that as you increase black hole kick strength, the number of black holes that you predict that fall in this nice Gaia observation window decreases by about an order of magnitude when you increase the kick strength. And that's because natal kicks in part of a big explosion in your binary that can unbind the system, and it does so more predominantly with low mass companions than it does with high mass companions. So the number of black holes that Gaia discovers is a direct correlator on the strength of black hole kicks. That's what we've got so far with our predictions. Okay, let's actually talk about real things though, because we can do that as well. I spent a lot of time getting ready for Gaia DR3 because it was going to be the savior of all of this. Gaia DR3 is when we got the binaries, and it kind of was. So we had a big party at Flatiron while I was a postdoc there, and the very first day, Kareem came in and made this version of this figure, where he plotted the semi-major axis projected of a star multiplied by its distance to get the size of the orbit versus the orbital period for every binary in the non-single star catalog. And you can see some nice features. These are all the normal stars. These are the weirdos that have anomalously large orbits for their period, which means that they are whipping around something more massive than anything else that's in this little data here. There's some cool features. You can see this is a 1-year feeding pattern that we just were really bad at measuring orbits there because parallax is at 1 year. You can't see anything that's overlapping there. Cool. You see the same type of thing coming in here. So Kareem actually had a pretty easy job, all things considered. There were 6 candidates that were like, definitely follow these ones up. So we did. The one with the star was the easiest one to find. And he used a bunch of data from lots of friends to do radial velocity follow-up, to make excellent mass measurements that he combined with the inclination measurement that comes from Gaia to get this constraint. I don't have error bars on this because they are stupidly small. Like there's no point in writing them down. They're tiny. There was a secondary candidate that he ended up continuing to follow up. That's Gaia DH2. This one. Same story, except much longer orbital period. Both of these systems are roughly 10 solar mass black holes, the same as every other one in our galaxy, basically, but with very low mass companions. Once we had this detection and we had a nice measured binary to play with. Remember how I told you we have a cool code? We use that cool code to map the joint combination of initial binary parameters with the common envelope ejection efficiency and the kick strength, to try to understand how did we make Gaia BH1. I'm gonna make this way bigger so you can see it. Don't worry. But we did everything jointly. The first thing that we learned is that alpha here, this is the common envelope ejection efficiency, is embarrassingly large by model perspectives. In particular, this is our formalism for common envelope ejection efficiency. What this says is that in order to eject an envelope with a given binding energy that we get from our simulations, you need some factor of the change in orbital energy that's available to eject the envelope. If you have an alpha greater than 1, there's an external energy source that's not the orbit. What we found for Gaia BH1 is, oh wait, I did it wrong. Alpha is something, it's not even 12.9 because this is like kind of skewed. It's like 14. 14 times more energy than there was in the orbit. So our models are bad for this is basically what we found. Or maybe our envelope binding energies are just catastrophically wrong. We're currently looking into this. We don't have an answer for you yet. But the other thing that we did do was measure the natal kick. And you can see our natal kick was constrained to be pretty low, 16 kilometers per second. If you compare that to the standard pulsar kicks of a Maxwellian of 265, which gives you something like 100, 200, 300 kilometers per second, tiny natal kick. So that's nice. And in particular, we prefer for it to be in the plane of the orbit. So I was excited to see that our models actually could cling to something on the measurement. So that was something nice. However, what I'll tell you is I don't believe that these systems form through isolated binaries because the alpha is just too much. It's too crazy. So we started to look for other different ways to do this. And in particular, with Ugo De Carlo, and then the same group actually uses kind of the same models. We looked at star cluster simulations to see whether we could make a Gaia BH3. These are fun dynamical formation exam. Oh wait, not BH3. Whoop. Spoiled myself. Gaia BH1, Gaia BH2. The spoiler here is that you kind of can make them, but not really. And the reason for that is because these star cluster simulations, all of them, are direct n-body calculations, which are fantastically expensive to run. And so we got one simulation, we went and looked in it, we're never gonna get another simulation of this size, and they don't match very well. So like, it's a big, like, if everything is star cluster formed in Gaia, that's my like demon sitting on my shoulder. That when I really should like not be stressing out, that he's sitting there being like, we'll never learn anything from Gaia. And I think it's because these n-body calculations are so difficult. Yeah.
So I was thinking about your large alpha and,
Oh,
it's
yeah.
not untypical of binary white dwarf, double white dwarf systems.
14?
10-ish, yeah,
Really?
yeah, and the story there is that it's recombination energy that's driving.
Do you think that that works in massive star envelopes?
Well, I was gonna say no.
Yeah,
And,
that's the thing
because
that I
the
worry
amount of
about.
Energy available as a fraction of the internal energy is so much smaller usually.
Yeah.
But, I was wondering two things. One was, you mentioned the binding energy maybe being overestimated.
Yeah.
And I was wondering, do you include inflation in your model?
No, but we could probably make a prescription that does that.
Yeah.
And I would love to do that.
Yeah, and
Yeah.
the other was jets.
Oh, boy. Model to put in with a tuning factor and I'll do it, but yeah.
But, and you know, this is something that Noam Zucker thinks is
Yeah.
everything. But you know, it's another way that you can get more energy than you can get from the orbit.
Right. Is jets worse than clusters? That's the question. Nobody knows, I think. Okay. Those, I appreciate, we should talk more, because I would love if the answer is we cannot have to do n-body. Like, it's so hard.
No, you only have to do common envelope simulations, right?
Easy. Good. Okay, with the negative time that I have, I'm gonna tell you one more thing, which is we have a third black hole, which potentially is the most exciting black hole of all. Gaia BH3. This was turned out by the Gaia collaboration itself because its orbital period is fantastically long, something like 12 years long. So it wasn't in the public data. They saw that Kareem was having all the fun. They went in and checked for themselves to see what else they could find, and they got this one. And oh my God, it's so exciting. In particular, very low metallicity, very, very low. Pretty big black hole there. Cosmic coincidence or maybe conspiracy. This matches with the LIGO mass bump. Weird, I don't know.
Well, you can
Yeah.
only get black holes that large with low metallicity.
Absolutely.
Single star evolution, so
Yeah,
maybe it's not that great.
so that tracks, but the question I have is, can we learn something from winds then? Because if we get a pile up at 33 to 35 from single star evolution, I don't know. So we're all in our conspiracy phase right now a little bit. But we don't have to do the channels conspiracy because this system has been localized to ED2, which is a disrupting globular cluster. We know that this thing wasn't a globular cluster, not because we did modeling, because we looked and it was in a globular cluster. You can't do that with gravitational waves. You don't get localizations like this. If you're gonna get a localization like this, you're gonna have to look with a telescope. So this is a lot of the reason why I'm going more towards telescopes right now, because it's really easy. The other thing that very quickly came out was that the cluster association does introduce opportunities for dynamical construction. Huge fan of Danny Marin Pina. I don't think that it has done this because the mass ratio is so crazy. There are papers being written right now that argue against that. And argue actually that it's a primordial binary where you just have to make your convection and rotation such that the binary doesn't fill its Roche lobe. On a 12-year orbit, that's actually not that hard to do. So that's probably what's happening. The thing that I will leave you with on the science part here is this. There are also a bunch of neutron star candidates. Gaia's doing it all. Gaia doesn't care about masses, so that's very exciting. But every binary that Gaia uncovers over the next 5 years will give us metallicity specific compact object parameters, which means we can really constrain our stellar evolution models because we know exactly the metallicity of the black hole that made this, and we can compare it to gravitational wave observations that don't tell us anything about metallicity to see if they're correlated. Gaia is one survey. I'll remind you here, basically all large scale surveys are gonna be finding these things eventually, as long as they're multi-epoch. SDSS5 is gonna be turning these things out. We're pretty sure that we can cross-match with TESS with photometric variability. Gravitational waves are doing this. All that needs to happen, ooh, look how cute. Cosmic comes in and connects everything together. So that's what I'm hoping to do over the next few years. And I'll leave you with my takeaways. And thank you for your patience for dealing with the 5 minutes over talk.
Thank you, Katie. Before we take questions, there was a question on Zoom from Stu Shapiro.
Oh, yeah.
Are you still there? Oh, can you read?
I think, oh, I can't.
Yes,
I can
I'm
read it.
still here. Yeah, a while ago, at the beginning of the talk, I asked about binaries like SIGX1, which is believed to be a wind-driven accretion object onto a black hole, but not one with Roche lobe overflow or common envelope evolution.
Yeah.
What about those guys? Or has the story changed?
No, I think that that's fair for SIGX1. I don't think that SIGX1 is like this big, beautiful, stable Rochambeau flow situation. I would say it's just a shorter period version of what we'll see with Gaia black holes. So it's just slightly closer such that the wind of the companion can be accreted and light up the X-rays. The other difference is that Gaia is less likely to see the big companion to a SIGX1 like no, that's not true. Never mind. It's definitely likely to see it. Are they? Yeah, actually, retract everything I just said about that last one. My brain wasn't working, but they are just in a detached state like you see here, but they're just wind fed.
Okay, thank you.
Yeah.
Paul, that's a great talk, really. Shoot. Oh, just forgotten my thing. Yeah, oh yeah, so BH3, its companion, the 0.76 solar mass. I mean, is there any spectroscopy of that star?
There's definitely follow-up spectroscopy.
Yeah, because what I'm wondering is, I mean, the naive expectation is just, it's a main sequence star, right?
Yeah, it is.
Maybe it's not.
Oh, like a merger?
Well,
Product,
maybe it's maybe it's a stripped remnant of the whatever companion there was. And so by looking at, you know, its spectrum, you could see whether it's
Right.
a helium star or it's a.
I think that they're pretty sure it's a main sequence star.
Okay.
Yeah. That would be sick if it is. I think actually, boy, y'all should have Maria Drought out. Let me just say that. I don't think I can build it in. What's the best way to show this? Maybe here. These guys, Maria Drought definitely in her strip star survey has these already. Strip stars with compact object companions. They're working on those papers now. Get excited. She's got this one and this one. So those are also gonna be amazing for us, and yeah. I wish that I had like a 10-hour talk to tell you all of these things.
So you said for BH3 that you were able to constrain this formation channel because you were able to figure out what environment it was in. Were
Yeah.
BH1 and BH2 not able to have that help?
Oh, yeah. Sadly, the answer is absolutely not. Let's see, we'll go here. You can do rotation, like gyro chronology, age measurements on these things, and they are at least 4 gigayears old. They're basically so old that those measurements don't mean anything anymore. That means that if they were in any type of cluster at all, long gone. They are completely mixed in the galactic population. They have very galactic disk-like orbits. Just like super boring. You could almost just like put the sun in where Gaia BH1 is and like you wouldn't even notice. Like it's the most boring star in the galaxy. Oh my God, other fun fact. You could put the sun here and the physical size of the orbit of the black hole is literally where the Earth is. Cosmic conspiracy. Yeah, just a fun thing, but. Yeah.
One question, let's say I go speak again. Well, interesting dinner, we'll be leaving here around 6 o'clock.
Yeah. Oh, dinner. Oh, yeah.